Ladies and gentlemen, welcome to my lecture on the consequences of fat tails in empirical work. So as a pre-requirement, I expect you that you have seen the lecture from Nassim Taleb at Cambridge University. I will also upload this lecture in Moodle, and that you are familiar with basic econometrics, basic statistics, and stochastic calculus. So this is not a lecture for undergraduate students, but for graduate students who know the basics already very well. So what we will investigate is in this lecture, we will talk about what happens if we face a fat-tailed distribution as opposed to a normal distribution, which is often used in empirical work, and also in order to derive different statistical properties, as for instance the properties of the ordinary least squares estimator. But first of all, what do many people do in empirical work? They just assume the normal distribution and then they run their analysis. But can we do that? Let's ask Nassim Taleb.
Reasoning error is not changing the color of the dress. The traditional approach by statistician has been, oh yeah, we know about fat tails. So for them, the illusion is that it's fat tails, oh, it's different, we have all these methods, we just assume a different distribution. No, 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 it's not how it works. You fall into logical inconsistencies. Because once you switch from the zone here, on which statistics was made up to here, okay, law of large numbers weak. You stop here, even below, you stop here. Once you get out of here, linear regression, doesn't work. A lot of things you think work don't work no more.
So obviously there are some problems if we assume the normal distribution, and this is what we will discuss now here on the whiteboard. So we have here, I plotted you three different distributions. We have the black one. The black line illustrates the standard normal distribution that has a mean of 0 and a variance or standard deviation of 1. Then I plotted you also here the blue line. The blue line should illustrate a t-distribution with 5 degrees of freedom. And finally, the red line illustrates a t-distribution with 3 degrees of freedom. So we know from statistics the properties of a t-distribution. So as the number of degrees of freedom decrease, the fatter are the tails. Yeah? And we have a different variance here. So the variance and the kurtosis, which is the fourth moment, they depend on the degrees of freedom of this distribution. For instance, here the variance requires that we have at least 2 degrees of freedom, and is defined as nu divided by nu minus 2. The kurtosis is defined as 3 plus 6 divided by nu minus 4. So the kurtosis obviously requires that we have at least 4 degrees of freedom. So you might remember when we discussed about simulation experiments, what people typically do is they typically use normal distribution, and then as one reference distribution for a fat tail distribution, they typically choose the t-distribution with 5 degrees of freedom. So when you read this book from Leslie Godfrey that I recommended you for this course, you will see that basically in all his experiments he has as reference distributions, apart from the normal, of course, he has the t-distribution with 5 degrees of freedom and the standardized chi-square distribution with 2 degrees of freedom for illustrating the effects of a skewed distribution. Yeah? So that's important to bear in mind. So what happens if we have a t-distribution that has less than 4 degrees of freedom? So, well, the kurtosis doesn't exist, and it means that the variance is sample specific. So the variance is unstable. We would need millions of observations in order to the variance to converge. And this is also what Nassim Taleb has been talking about in his lecture at Cambridge university. Yeah? So the law of large numbers simply doesn't hold anymore, or it doesn't. We don't have enough observations so that the variance converges. Yeah? So that's the big problem, but we will talk about this later. So let us now assume, let's consider the variance. So the variance of these distributions. So we just have to plug in, if we have a t-distribution with 5 degrees of freedom, we just need to plug in what it is, 5 over 5 minus 2. So we come up with the figure of 1.67. So as what we see here is, as the degrees of freedom, as we move from the normal distribution to the t-distribution, as the degrees of freedom decrease, the variance increases, obviously. Yeah? So 1.67 is obviously 67% larger than 1. Yeah? And 3 is almost 2 times larger than 1.67 and 3 times larger than the variance of the normal distribution. What we also hopefully remember from statistics classes is that we can, if we have an infinite number of degrees of freedom, the t-distribution, it breaks down to the normal distribution. So if we have, let's say, 200 degrees of freedom, we can simply use the critical values of the standard normal distribution for the t-distribution. Yeah? So that's important to bear in mind. Yeah? So that's the link between the t-distribution and the normal distribution. So the variance increases as the number of degrees of freedom decreases. What about the kurtosis? The kurtosis of the normal distribution is 3. The kurtosis of the t-distribution with 5 degrees of freedom, if you plug it in here, you will see that we have a kurtosis of 9. So whenever you have data, you upload the data and you get the descriptive statistics out of your program, and the kurtosis indicates a value that is larger than 3, the likelihood is high that you're not dealing with a normal distribution. Okay. So what's the kurtosis of the t-distribution with 3 degrees of freedom? So obviously we see here, that the t-distribution with 3 degrees of freedom has a kurtosis that is not defined, or it's infinite. So again, what does it mean? It means that the variance, even though the theoretical variance exists, as we see here, it's 3, but in real life we don't observe it. Any sample that we have will give us a different estimate of the variance. So we cannot use it simply. The variance, we cannot use a sample-specific variance because obviously we end up with wrong estimates for the t-statistic. So we cannot do hypothesis testing, as simple as that. So let's have a look what happens if we move on the x-axis -1 and +1 standard deviations. So this is obviously an important metric. The standard deviation is well defined for the normal distribution, and the normal distribution is probably the only distribution that has 68.26% of the probability mass, of the probability density, if we move -1 and 1 standard deviations on the x-axis. So that's well defined. 68.26% probability is within -1 and +1 standard deviation. So what about the t-distribution with 5 degrees of freedom? So obviously the standard deviation is the square root of 1.67. So we have to take the square root of 1.67 and -1, which is 1.29. So in terms of standard deviations, if you want to investigate what happens within this move from -1 standard deviation to +1 standard deviation. So what we have to consider is obviously we have to move -1.29 steps to the left and +1.29 steps on the right. And we have 74.72% probability density within these bounds. So simply because obviously the variance is larger, so obviously we have to take a little bit larger steps also for figuring out what happens between -1 and +1 standard deviations. as we move to the t-distribution with 3 degrees of freedom, what happens here? So the variance is 3. We have to take the square root of 3 in order to get one standard deviation, which is 1.73. So in order to know what happens between, or how much probability mass is between -1 and +1 standard deviation, we have to take the integral, obviously, from -1.73 until 1.73, and then check how much probability do we have here in the red curve. And that's obviously 81.83% probability. Yeah? So we see that this is exactly what Nassim Taleb was talking about in his lecture at Cambridge University. So as we decrease, as we fatten the tails, so obviously the t-distribution with 3 degrees of freedom has much fatter tails as illustrated here, as the t-distribution with 5 degrees of freedom or the normal distribution. Yeah, we see there's more probability mass here in the tails, and we see that we have more observations in the middle. Yeah, so we have more observations in -1 and +1 standard deviations, yeah, from the center of the distribution. So this is where what most people obviously get wrong. They think there are less observations in the middle. And the problem, the logical inconsistency that happens obviously is that if people assume the normal distribution. Yeah? So if you think this distribution, the blue line here, which is actually a t-distribution with 5 degrees of freedom, if you think this is normal, and you compound what happens between -1 and +1 on the x-axis, as opposed to -1.29 and +1.29, which is the real standard deviation. But if you take the standard deviation of the normal distribution instead, what you will see is that 63.68% is within these bounds, given we have the blue line. And the same is for the t-distribution with 3 degrees of freedom. If we take the standard deviation of the normal distribution, which is -1 and +1, and we take the integral from -1 to +1 for the red line here, which is the t-distribution with 3 degrees of freedom, what we see is that only 60.90% is within -1 and +1. But that's obviously wrong, because the actual distribution has much, much more observations in one standard deviation if we take the real standard deviation of that distribution. Yeah? So we make obviously a huge error. The error increases as the number of freedom decreases. So as we have fatter tails, more impactful tail events, this is what it means, we obviously underestimate what happens within -1 and +1 standard deviation if we think this distribution has thin tails. Yeah? So if we now take the next step, if we check, okay, what happens if we move 2 standard deviations to the left and 2 standard deviations to the right. Yeah? So we see if we have the normal distribution, we have 95.42% probability between -2 and +2 standard deviations. So this is usually, that's why we have usually in statistical tests, we have this, you might remember, we use the critical value of -1.96 and 1.96. There we have exactly 95% probability. Or in empirical work, you just compare your t-statistic with 2. So if it exceeds 2, obviously you know that on the 5% level, you would basically reject the null hypothesis because the observation is too far away from the center. So that's the reason for why we have this, for why we perform our hypothesis test using a value of 1.96 respectively. In applied work, it's usually 2. So what happens if we consider the t-distribution? Surprisingly, so if we take 2 standard deviations using the real standard deviation, which is 1.29 1.29. So you have to take now minus 2 times minus 1.29 until 2 times 1.29. Yeah? And in these boundaries, we have 95% of the probability, which is very close to what we see for the normal distribution. Yeah? And similar for the t-distribution with 3 degrees of freedom. So what we do have to do now is we have to take the integral here for the red function from minus 2 times 1.73 until 2 times 1.73. Yeah? So, and this integral, we have obviously 95.95% of the probability mass of the t-distribution with 3 degrees of freedom. So obviously, what happens in 2 standard deviation space, given we have the correct number for the standard deviation, we see it's pretty much the same thing. Yeah. If we would think, however, if we would treat this distribution, the t-distribution with 5 degrees of freedom, as a normal distribution, we would believe, or what we get is, we would get 89.81% of the probability mass instead of 95%. And for the t-distribution, the difference is even larger. So if we take the standard deviation of 2 from the normal distribution, so if we check, okay, what happens between minus 2 and plus 2, but we take the integral not for the black line but for the red line, what we see is we have 86% of the probability mass in these boundaries. Yeah? So we underestimate what happens, what really happens in minus 2 and plus 2 standard deviations of the real underlying distribution, obviously. So what happens is that obviously what happens in the real distribution will come to us as a surprise, because we underestimate what happens. So that's the big problem. And if we consider now the t-distribution with 3 degrees of freedom, and we take a move of 6 standard deviations, so we have to take 6 times this number here. If we think this distribution is normal, we would think this is a 10 sigma move. So which is obviously much less likely. So we obviously we run up into errors. So we underestimate the occurrence of extreme events, which we see here. This is a very good example, a very good illustration to my mind. As we underestimate the occurrence of extreme events if we treat these distributions here as normal, as opposed to what it is, which is a t-distribution that has much fatter tails. So that's an important thing. So once again, to summarize what we have learned here, so as we fatten the tails, less and less observations are in the space between -1 and +1 sigma or standard deviations of the normal distribution. We see that the observations between -1 and +1 decrease, but more observations are in the real -1 and +1 sigma. We see that the observations that are in between -1 and +1 sigma of the real distribution, if we take the correct variance, there are much more observations in this -1 and +1 sigma. So as the tails are fatter, more observations are in the between -1 and +1 sigma of the real distribution. So extreme events, if we take the wrong distribution, they will come as a surprise because we don't expect them. So what will we do next? Next we will investigate what happens on the covariance matrix of the ordinary least squares estimator if the distribution is fat-tailed as opposed to thin-tailed. Let us again assume that we have this standard model, a linear regression model, where our dependent variable yt is dependent on an intercept term alpha plus beta 1 times regressor x1 t plus beta 2 times the regressor x2t plus beta 3 times the regressor x3t, and we have this error term. Yeah? And we know already from our lectures that we always have to check the error term, so we have to know if the error term is well behaving. Again, we assume that the expectation of the error vector, of the residual vector, and our regressor matrix is 0. So we assume we do not deal with a dynamic model, so we assume that our regressors are exogenous, and we know already this is only for didactic purposes. We know if the regressors are uncorrelated with the residuals, we have the same outcome when we derive the properties of the point estimator or the covariance matrix. We have already seen that. So given this framework, we have our well-known point estimator beta hat, which stacks the estimates for alpha, beta 1, beta 2, beta 3 into a 4 by 1 vector, and this 4 by 1 vector is defined as the regressor matrix x transpose x inverted times x transpose y. So the interesting thing is now we know when we have derived the point estimator, so we know if we take the expectation of our point estimator beta hat, so it didn't really, the distribution of the residual vector doesn't matter to show that the point estimator is unbiased. So the expectation of our point estimator beta hat is beta, irrespective if we have a different distribution for our residual vector. So let us now assume that we are dealing with a t-distribution with 5 degrees of freedom. Let us assume that our error term ut follows a t-distribution with 5 degrees of freedom, and this distribution is IID. So it's identically and independently distributed. So what happens to our term? So we remember that this guy here, if the distribution is identically and independently distributed, we can rewrite the covariance matrix. So what we have here in the on the main diagonal are the sigma squares. Right? You might remember that when we made our derivation, and above and below the main diagonal there are zeros. We have done this a couple of times in our course, so this does not come to you as a surprise. And you might remember that we can remove this sigma square outside this matrix here. What remains is an identity matrix that has only once on the diagonal, which is a t by t matrix. And we know that this expression here then simplifies to covariance of our beta hat estimator is simply given by sigma square times x transpose x inverted. This is what remains from this expression here. So the point is now knowing that the variance of our t-distribution with 5 degrees of freedom is 1.65, or we remember that sigma square is defined as mu over mu minus 2, and if we have 5 degrees of freedom, we have to plug it in. So what we get is that sigma square is 1.67. So what we also know is, we talked already about this earlier, if we have a t-distribution with 5 degrees of freedom, obviously bootstrapping works very well. Yeah? So that's obviously no problem. Yeah? We just have to see now that this guy here is now, given we know that the underlying distribution is t-distributed with 5 degrees of freedom, this sigma square is larger than 1. Yeah? It is larger as if it would be normally distributed with 0 and 1. Yeah? But otherwise, obviously, the important point here is that, first of all, it's independently and identically distributed, yeah? Which means that any element here on the main diagonal has the same variance, and we can move the variance outside, and it's just a number, obviously, it's 1.67, and this overall expression from the covariance matrix breaks down to the standard expression that we know before from earlier courses. So the only thing that changes here is obviously that the sigma square is different, given we know that the underlying process is t-distributed with 5 degrees of freedom. So, but what happens if this process is distributed as a t-distribution with 3 degrees of freedom? So this obviously happens often in, or often, there are obviously scientific papers that report that we can approximate stock returns, daily stock returns, by a t-distribution with 3 degrees of freedom. Yeah? So obviously what happens here, the variance is defined. So the variance, obviously, as we have also derived on the whiteboard previously, the variance is then obviously 3. It's 3 over 3 minus 1, which is 3. Yeah? So the variance is defined, and obviously what happens here, the same thing happens, because it's identically distributed and independently distributed, and the variance is defined. We can do the same operation, but then obviously here, what changes here is that our variance is now 3. But it increases. But what happens to our point estimator? Yeah? So the question is now, okay, can we do statistical inference if we have a t-distribution with 3 degrees of freedom as the data generating process of the error term? So obviously, even though in theory the theoretical variance is defined, in real life it's sample specific. In real life we do not observe it. So even though we come to the conclusion that our residual process is fat-tailed and is best approximated by a t-distribution with 3 degrees of freedom, so the variance that we observe in the sample will never be the real variance of the process. Yeah? So it will be sample specific because the kurtosis is infinite. And this is what we have already, what we knew already from the previous analysis. If we have a t-distribution with 3 degrees of freedom, the kurtosis, which is in essence the variance of the variance, it doesn't converge. It does not converge, so the variance will be sample specific, and what means, and this means is that our covariance, our estimated covariance of the point estimator will be different in each sample. So we are not allowed to make statistical inference because the statistical inference is misleading. It will always be different if we change the sample. So t-statistics in real life or in applied work do not tell us anything about the accurateness of our point estimators in this scenario. Moreover, bootstrapping obviously does not work either because of that problem. And this is also a thing why obviously in the literature that deals with bootstrapping, they usually stop at the t-distribution with 5 degrees of freedom because of this issue. Yeah. So Taleb, in his book, which you also are supposed to read, the 3rd chapter in his books on the statistical consequences of fat tails and on pre-asymptotics. So he argues that even the t-distribution, even if we allow for t-distribution with only 3 degrees of freedom, obviously it does not generate the fat-tailedness that we observe in the real life. And in his book, he argues that power laws, or Paretian or Pareto distributions should be the norm. So this is what he argued. So obviously we cannot model real fat-tailedness, what we observe in certain economic variables or social science variables, by the t-distribution. Moreover, the t-distributions, obviously, it's a symmetric distribution, but if we think about, for instance, cyber attacks, Bitcoin hackings, or market capitalization, all these things that we, book sales, all these things that we discussed when we were talking about the Black Swan book. So all these variables, they have only one side. They are distributed like this. So it's not symmetric distributed. So in these circumstances, we usually would model the process by using a power law process. And this is also what we will talk about in what follows. Moreover, we can also, of course, we can approximate, we can model a two-sided process. We can have, if we have a power law process, we can model basically both tails by using power laws. If we choose the same probability, we have a probability of p and probability 1 minus p, and then we can define, we just have to multiply, we can define two processes and multiply the one side with -1, then we have basically the corresponding outcome for the other side of the distribution, right? So that's not a problem. So what role play power laws or Pareto distributions in real life? So we have already talked about economics and especially financial economics. What about other disciplines in social science? So let us listen to what Dr. John Peterson, who is professor of psychology at the University of Toronto, tells us about the applications of Pareto distributions or power laws in psychology.
So there's the distribution of scores. Now that's dismal. That's a dismal thing to look at. You have to understand that. Why? Look at this. 0, right? The median person has not done anything creative ever in their life with anything on any dimension. Right? It's really important to know that. And then you have these horrible people out here. Right? They do everything. They do everything. Price's law. Here's Price's law. This is something to hammer into your heart. The square root of the number of people in a domain do 50% of the work. Okay, so let's go through that. You have 10 employees. 3 of them do half the work. Makes sense. That's reasonable. You have 100 employees. 10 of them do half the work. Well, that's a problem. So the other 90% are doing the other half. Who cares about them? You have 10,000 employees. 100 of them do half the work. Right, so here's a nasty little law. As your company grows, incompetence grows exponentially and competence grows linearly. Got it? Right? Because with 10, it's 3 who are doing half the work, but at 10,000, it's 100 that are doing half the work. So 9,900 of your employees are doing as much as the best 100. You might not even know who the best 100 are, but probably they know. And maybe their peers know too. And so one of the things that's really interesting when big companies start to shake, which means maybe they've had a bad quarter or 2 bad quarters, and the stock price starts to tip down, and the people, the hot people who have options are not very happy about that, and maybe they start to announce layoffs, all the 100 people who have opportunities leave. And they're the ones who were doing half the work. So boy, that puts your company in a pretty rough situation, because now you've got the 9,900 people left over who were only doing half the work. And the next time you announce layoffs, the next most productive 100 leave. And so then you're left with nobody who's productive and a massive overhead payroll. Price's law, you can look that up. De Sola Price. De Sola Price is a guy who was looking at scientific productivity. And one of the things he found was, when he was looking at PhD students, is that the median number of publications for a PhD graduate when he did his work, which was in the early 60s, was 1. Okay, half as many had 2, half as many as that had 3, half as many as that had 4. It's a real step down. And one of the corollaries of that is that there's a certain number of people who are hyperproductive, and that's these people out here. And if you were graphing the distribution, let's say you graphed how many people in a population of 300 had $10,000 in a savings account. It would look very much like this. Some of them would have, or some of them would, most people would have like no savings whatsoever. The median person would have no savings whatsoever. And then you go up here where the 1% is, they have all the money. But the thing you want to understand about that 1% issue that you always hear about is that it applies in every single realm where there's difference in creative production. Every realm. Doesn't matter. Number of records produced, number of records sold, number of compositions written. So here's an example. 5 composers produce the music that occupies 50% of the classical repertoire, right? Bach, Beethoven, Brahms, Tchaikovsky, Mozart, that's right, those 5. Okay, so here's something cool. So you take all the music those people wrote. 5% of the music all those people wrote occupies 50% of the music of their writing that's played. So not only do almost all the composers never get a listen, but even among the composers who do get a listen, almost none of their music ever gets played. So then that's another example of this Price's law of scaling. So it applies to all sorts of things, like number of hockey goals scored is also distributed this way. Number of basketballs successfully put through the hoop follows the same distribution. Size of cities follows the same distribution. It's a weird law, and you can think about it in part. Why does this happen? Well, imagine what happens when you play Monopoly. What happens? Everybody has the same amount of money to begin with, right? So then you start playing. It's basically a random game. Well, some people start to win a bit, and some people start to lose a bit. And then if you win, the probability that you'll keep winning starts to increase. And if you lose, your vulnerability increases as you lose. And then maybe you've got, say, 6 people playing Monopoly. Soon one person has 0. What happens when they have 0? They're out of the game. So 0 is a weird number, because when you hit 0, you're out of the game. So then if you keep playing, people start to stack up at 0, right? What happens at the end of the game? One person has all the property and all the money, and everyone else has none. Right, that's what happens if you play an iterated trading game to its final conclusion. And that's part of the law, in a sense, that's underlying this kind of distribution. So it's not a consequence necessarily of structural inequality. It's built into the system at a deeper level than that. So, you know, people talk about all the time about how unfair it is that the 1% of the population has the vast amount of the money, and 1% of the 1% has most of that money, and 1% of the 1% of the 1% has most of that money. But it is it's an inevitable conclusion of iterated trading games, and we don't know how to fight it. We don't know how to take from the people who have and move it to the bottom without it instantly moving back up to the top. Different people maybe, but still back up to the top. Because even the 1% churns a lot. Like I think you have a 10% chance, if I remember correctly, you have a 10% chance of being in the top 1% for at least 1 year of your life, and a 40% chance of being in the top 10% for at least 1 year in your life. That's in Canada and the US. It's less so in Europe. So there's a fair bit of churning at the top end. It's not the same people all the time who have the money, but it is a tiny fraction of the people all the time who have all the money. One of the things that you'll find if you look at creative production in any domain, it doesn't matter, artistic domain, food production, novels written, novels sold, money generated, number of companies generated, number of goals scored in hockey, etc. Or number of paintings painted, number of compositions written, anything like that, where the fundamental underlying measure is human productivity, what you find is that a very tiny percentage of people produce almost all the output. It's called a Pareto distribution, P-A-R-E-T-O, and it was studied in detail in scientific productivity by someone named de Sola Price. It's a square root law, so here's the law fundamentally. If you look at the number of people who are in a given domain, who are producing in a given domain, the square root of the people produce half the product. So that means if you have 10 employees, 3 of them do half the work, but if you have 10,000 employees, 100 of them do half the work. Right? It's a very, very vicious statistic. And you won't learn about that in psychology for reasons I have no idea about, because you learn about the normal distribution and not the Pareto distribution. But Pareto distributions govern, for example, the distribution of money, which is why 1% of the people in the general population have the overwhelming amount of money, and 1/10 of that 1% has almost all of that. Right? So I think it's like the richest 100 people in the world have as much money as the bottom 2.5 billion. And you think, well, that's a terrible thing, and perhaps it is, but what you have to understand is that that law governs the distribution of creative production across all creative domains, right? It's something like a natural law, and we'll talk about that more, but imagine what happens when you play Monopoly. You've all played Monopoly. What happens when you play Monopoly? One person ends up with all the money, all right? Then you play another game of Monopoly. What happens? One person ends up with all the money. It's actually the inevitable consequence of multiple trades that are conducted randomly. So if you take 1,000 people and you get them to play a trading game, you each give them $100, say, or $10, and they have to trade with another person by flipping a coin. I win the coin toss, you give me $1, you win, I give you $1. If we all play that long enough, one person will end up with all the money and everyone else will end up with 0. So it's a deeply built feature of systems of creative production, and no one really knows what to do about it, because of course the danger is that all the resources get funneled to a tiny minority of people at the top, and a huge section of the population stacks up at 0. But to blame that on the oppressive nature of a given system is to radically underestimate the complexity of the problem. No one actually knows how to effectively shovel resources from the minority that controls almost everything to the majority that has almost nothing in any consistent way, because as you shovel money down, it tends to move right back up, and it's a big problem.
Let us now derive the power law. So the power law is defined as a process with a survival function, probability of capital X is larger than X, which is equal with P from X, is equal with capital C times x to the power of -1. We can rewrite this expression here. Obviously, we can put this x to the power of -1. If you put it into the denominator, the exponent becomes positive. So it's the same as c over x to the power of alpha. And our x is defined for values that exceed a certain minimum value. So the minimum value is obviously very important for the definition of the power law process. And this is why this is so. So we have on the x-axis the outcome of the random variable that bends the power law. And we have here on the y-axis the probability. And obviously, so we need some minimum value where the power law bending process begins. So not all variables are bending the power law, and in real life, obviously, we have if we have a distribution and we investigate the underlying distribution, we might figure out that a certain percentage, let's say 70% of the distribution, do not bend the power law. So we can approximate the sample mean. We can operate with the sample mean, but for the rest of the distribution, let's say 30% of the distribution or less, they are bending power law, and then we have to operate with them differently. So obviously, in order to make this function here a probability function, we have to perform the normalization. So every probability function has a probability density equal with 1. So we have to set this function here equal to 1. So, and again, the function begins with the x minimum value and it goes to infinity. If we have, obviously, we have fat tails. So obviously, if the support of the function goes from x minimum to infinity, we have to take the integral from x minimum until infinity, and this should be equal to 1, given our function p from x. And we know from high school math how to operate with integrals. So what we have to do is first we have to just to plug in the function as we have defined it here as our p from x. We take the integral, and we know from integral calculus, because c is a constant, we can move it outside the integral operator. Like the sum operator, they work very different, very similar. So we can move this constant term outside the integral. What remains is the integral is c times the integral from x minimum to infinity from dx over x to the power of alpha. We can now rewrite this expression here. So we know that our dx actually, we can also write it like this, and we know that this expression here is nothing else. If we take the, we can rewrite it as x to the power of minus alpha. This is what it says, and this is what we have done here. So we take this integral. Now we have to ask, what's the derivative? So what's the derivative so that we end up with this expression here? So, and that's obviously what happens here. So the derivative is obviously this guy here. If we take the derivative of this expression here, we end up with x to the power of minus alpha. But what we have to do is, obviously, we have also to move in the c, the constant term, in it. And now we have to solve this expression here from x minimum until infinity, because our integral is from x minimum to infinity. So what happens? So we know now what we have to do from high school. Now we have to plug in what is here in the upper part first, and then we have to subtract the lower part. We have to plug in the lower part here into our x and then subtract it. So this is what happens here. So obviously this part here, if x goes to infinity, this goes to 0. This part disappears. So it's 0 minus what? Now we have to plug in x minimum here in our operator. And this is what comes out. So it's 0 minus c over 1 minus alpha times x minimum, our minimum value, to the power of minus alpha plus 1. So again, what do we have to do? We have to, because we want to perform the normalization, we have to put it to the power. We have to put it equal with 1. We have to put this expression now equal with 1. And this is the same. What we can do now is we can move this guy here to the other side. We can just multiply it. We multiply both sides of the equation with 1 minus alpha. What happens then is we have 1 minus alpha on the left-hand side, and what remains is our minus c times our x minimum value to the power of minus alpha plus 1. What happens then next is we can multiply both sides of the equation with minus 1. So we change just here the signs. So this becomes positive here, obviously, and here we have to change the sides. So 1 minus alpha times minus 1 becomes alpha minus 1. So what happens next is we want to solve the equation for the c. We are interested in the value for the c. What has the c to be in order to make it a probability function? So next we bring what is here, this x minimum to the power of minus alpha plus 1. We bring it to the other side of the equation. So we have to divide what is on the left-hand side of the equation by this guy. This happens what happens here in the next step. So we solve this equation for c, and we end up with c is equal with 1 minus alpha, alpha minus 1, divided by x minimum to the power of minus alpha minus 1. So, and that's basically how it works. Now we are ready. Yeah. So we can, we have defined our alpha. What is our c? Now we can just plug it in for in our power law, and what we end up with that our probability function is defined as alpha minus 1 times the minimum value to the power of alpha minus 1 times x to the power of minus alpha. So now we have derived the probability function for our power law process, and when you study the literature, you will see that there are obviously different definitions of this equation or of the power law process. And in my notation, I follow the paper from Aaron Clauset et al., which is also in Moodle in the reading list. Yeah. So what happens next is, okay, once we have defined our probability function, let us have a look at the moments of that function. So let's have a look now on the moments of that distribution, the power law process. Again, the power law process is defined as c over x to the power of alpha. So for the first moment, what's the first moment? So it's the expectation of x, and it's defined as the integral from the lower bound x minimum until infinity from x times p from x dx. Yeah? And this is the standard definition of the expectation of a continuous function. Yeah? So what we have to do now is, in order to solve this integral, we have to plug in for p from x our probability function that we just derived. We know that it's c over x to the power of alpha. We just plug it in. This is what happens here. We can move again the c, which is a constant term, we can move it outside the integral operator. And what we also know is that x, we can add here 1. X is simply x to the power of 1. And we can move these together because the basis is the same, it's x. So what we have then is x to the power of 1 minus alpha. And again, c is outside the integral operator. So we have to solve this integral here. This is basically the next step. So we have to think about what is the underlying function from which this is the derivative. Because that's basically how our integral, how we can solve this integral. And if we figure this out, so if we take the derivative of this function here, we end up with x to the power of 1 minus alpha. So that's obviously the underlying function here. Again, our c is still outside the integral operator, but we can move it in again. So we can likewise move the c here in, and we have to take it away from here. This doesn't matter, it's just a constant. So what we have to do is, again, how do we solve this integral? So again, we have to plug in what is here on the upper bound into for our variable x, and then we have to subtract it from plugging in what is here for the x. This is what happens in the next step. If x is infinite, the whole expression here becomes 0. It's 0 minus plugging in x minimum for x. What happens here is we get this expression, c over 2 minus alpha times x is now x minimum to the power of 2 minus alpha. So now we know from our previous analysis that c is defined as alpha minus 1 times x minimum to the power of alpha minus 1. We plug in see for what it is, and we end up with this expression here on the right-hand side. So again, we have to remember now that we can simplify this expression because x minimum pops up here twice. So we can simplify this expression, and what remains is alpha minus 1 over minus, in parentheses, 2 minus alpha times our x minimum value. We can simplify this even further, and what remains is alpha minus 1 over alpha minus 2 times our x minimum. So obviously we see that the expectation, the first moment, which is the first moment of the distribution, only exists if our alpha is larger than 2. So the first moment only exists if alpha is larger than 2. This power law exponent, this alpha, captures, according to Nassim Taleb, the extreme event. It captures the extreme event. So the lower the exponent, the more extreme events we can observe in the data. So if the alpha is, let's say, 1.5, our distribution has no mean, obviously. So what we can do next is, so this is very, very important to bear in mind. The expectation, the first moment, is only defined if the exponent is larger than 2. Otherwise, our distribution has no mean. And now you may wonder, okay, do we have distributions in real life that have no mean? The answer is yes, we have. And if you study the literature, there are actually quite many distributions. For instance, the paper from 2020 from Kirillo and Taleb, they estimated the risk of contagious disease such as COVID-19, and obviously this distribution has no mean either. So obviously it's tricky how to deal with distributions that have no mean. I mean, obviously this is a very special case of distributions, and we will come back to that later on. But what we have to bear in mind now next is, so if we can, in the same manner as we derived the first moment, we can also derive the second moment. The second moment, obviously, is the expectation of x squared, which is in essence the variance. What we have to do is we have to take the integral from x minus until infinity x squared times our probability function p from x dx. So, and this is what you can do, or what you should do as your homework. So what you will see is, if you solve that in the same manner as we solved it for the first moment, if you apply the same approach, what you will see is that what comes out is alpha minus 1 over alpha minus 3 to the times x squared minimum. So obviously the second moment, which is the variance, is only defined if the exponent is larger than 3. Moreover, the kurtosis only exists if alpha is larger or equal with 5. So that's also very important to bear in mind, because we know already, we discussed this earlier, if the kurtosis does not exist, even if the theoretical variance exists, we cannot operate with a t-statistic because it will be sample specific. So that's obviously a huge problem here. And again, we have to bear in mind that we can only operate with distributions, yeah, that have a finite kurtosis. Yeah. So that's important to bear in mind, yeah, that you know, okay, the alpha captures the alpha captures the low probability event. So if the smaller the alpha, the more impactful will be the extreme event. And we have seen in this one figure when we discussed the Black Swan book. So Nassim Taleb gave obviously for different real life phenomena the corresponding exponent, yeah? And if the exponent is close to 2, yeah, there is the 1% of the distribution. If the exponent goes to, is let's say 2.001, yeah, and we would simulate the distribution, what we would figure out is that 99% or so, yeah, of the distribution, of the cumulative distribution is summarized by only 1% of the largest, most impactful events. So that's the trademark of this kind of distributions. If we have a very low exponent, it means that a few observations correspond or make the largest part of the overall cumulative distribution. So that's the big difference between this very fat-tailed distributions and as opposed to thin-tailed distributions like the Gaussian. So the next question that arises is how do we estimate this distribution? If we study the literature, what we will recognize is the so-called maximum likelihood estimator for the power law function. And also, if you remember that Nassim Taleb, during his lecture at Cambridge University, he said that maximum likelihood estimation, it works. So given we have a data set, so what we can do is we can estimate the corresponding alpha using this formula, which is the so-called maximum likelihood estimator. So it's 1 plus n, which is the sample size n, and what we have here is apparently is where we sum up from I is 1 until n, and what do we sum up? We take the logarithm of the values xi divided by x minimum, and we do that. After we did that, we take the inverse. So we can also rewrite this expression here as 1 plus n over this sum from I is 1 until n, the logarithm of xe over x minimum. Yeah. So that's basically how it looks like. So, and how do we proceed? So basically we have a data vector, let's denote it as x. We have our observations here, observation 1, 2, until n. So let's say this is an n by 1 vector. So, and what we do is we sort this vector from largest until smallest observation. So we say, okay, let's in the first trial we take the smallest observation as our x minimum. We have obviously all observations here in our sample then. So n is then equal to to n, and we get an estimate for our alpha, yeah? Which is then the first estimate. We do it again, and we take the next smallest item, the next smallest observation. That's then our x minimum. Then we have obviously here one observation less. Yeah? So we have to divide it then by, or we have here n minus 1 in the denominator. And here this sum sign also goes from the second observation then obviously until n minus 1. Or actually it remains n, right? Because if that's our second observation here, that's our nth observation, so it goes until n, of course, yeah. But it starts at I is 2, and we have to, obviously, in the denominator, one observation less. So, and we get then our alpha hat 2. And in the same way, we go through the whole vector, yeah. So we have to stop, obviously, here somewhere. Usually, what I do in empirical work, I stop, let's say, at n minus 5 or so. Yeah, so I go step by step until n minus 5. I get obviously a whole series of estimates for these alphas. Yeah, and obviously I have less and less observations here, yeah, in the denominator. Yeah. So this is basically what we have to do. We have to do it iteratively, yeah, because obviously the alpha, the exponent, the estimated exponent depends on the minimum value, and it changes, yeah, obviously. So what we will typically see is, if we, because we have to do it for this sorted vector, what we will typically see is we plot it then, we can plot that, we can plot the alpha is then on the y-axis, and our x minimum is on the x-axis, yeah, and there we can basically see how the evolution of the alpha looks like, yeah, and usually what you will see is something like this, and the optimal value for the alpha is then usually the saddle point of that function, yeah. So we can basically read what's the optimal alpha and the corresponding optimal x minimum value. Yeah, let's denote it as as alpha hat star and x minimum star. So we can read it from this plot here, from the alpha hat x minimum plot, which is often called the hill plot. The hill plot. Obviously, there are also other possibilities how we can get the optimal alpha hat given our data vector, but this is something that I will probably not cover in this lecture because I have obviously a limited time available. But this is basically what one possibility, what people often do in applied work. Yeah, they estimate successively the alphas, yeah, given they start with the smallest n, with the smallest observation in our sorted vector, and then they move on to higher observations, to larger observations, re-estimate the alpha. We get always a new alpha, and we have less observations, obviously, to estimate it. And then we can store the values for the alpha and the corresponding minimum value for x from our vector, from our data vector, and then we can plot it. Yeah, we can plot the estimated alpha hat against the corresponding x minimum value. Then we know which observations basically, which observations in our data vector bend the power law. Yeah, and maybe it's until here. Maybe we will figure out that the power law is valid for these largest observations, which are maybe, let's say, 20% of the sample or less, and the rest of the data vector follows some other distribution, maybe even a normal distribution. Yeah. So that's basically how we would proceed in practical work. And the last question arises, how can we simulate a power law distribution? Yeah? This is how we estimate it, given we have a real-life data set. Yeah? Now the question arises, the last question that arises for this lecture or for this course, how can we simulate a power law distribution knowing the parameters? Let us now have a look at the simulation. Yeah? How can we simulate a time series or an evolution of a power law process given we know the x minimum value and the corresponding power law exponent alpha? So it took me quite some time to figure this out. Obviously there is no information, no proper information in the internet. At least I haven't found anything, so I was supposed to go through it by myself. So that's basically how it works. So obviously we are interested in solving this integral here. So we know that our power law process from x minimum, if you take the integral from x minimum until infinity, that's 1. That's obviously per definition, and we have to solve. We are looking for the corresponding value of x from p from x. Let's say we want to have this value here. So how do we get this value? We have to ask the question, what's the corresponding value of x that solves this integral? That's the question. And we know it's 1, because 1 is the probability from x minus 2 into the right side until infinity, and the probability, we have to take the probability from that, which is 1, minus the probability of what is here. And this is basically the part that is here marked in blue. That's the probability, that's the corresponding probability, and we are looking for the value of x from p from x that fulfills this requirement. So if we solve this, these are many steps obviously, and we'll not make the full derivation here, but you should do it at home. And what you should come up with is this expression. So the corresponding value x from p from x, what is it? It's defined as our x minimum times the probability p from x times minus 1 over alpha minus 1. So now we can, if we have we just need a random number generator that gives us random numbers between 0 and 1 in terms of probabilities. So and using these random numbers, we can easily estimate the corresponding value for our power law process, the corresponding realization of the x variable. Because if we know the minimum value x minimum and we know the alpha, all that is random here is the probability p from x. That's what we get from our random number generator, so we can use that, and we get the corresponding, plugging this in, we get the corresponding value that fulfills this equation. So that's how we can basically operate with a power law process, and we can simulate the process, and we can play around with that and see what happens in the tails of the corresponding distribution. So what we will do next is we will have a look at the data sets, and we will run it in our program, in our MATLAB program, and we'll see how to use our derived equations in a real-life data set.